happy to have Professor Yasuo Cho here from Tohoku University, the new industry creation Hatchery Center. Professor Cho graduated in 1980 from Tohoku University, electrical engineering. 1985, he became a research associate at the Research Institute of Electrical Communication at Tohoku. In 1990, he received an associate professorship from Yamaguchi University, then became an associate professor in 1997, and a full professor in 2001 at Research Institute of Electrical Communication at Tohoku University. During this time, main research interests include nonlinear phenomena in ferroelectric materials and their applications, research on the scanning nonlinear dielectric microscopy, and research on using scanning nonlinear dielectric microscopy and next generation ultra-high density ferroelectric data storage. Today he's here to present his talk titled Recent Progress on Research and Development for Practical Application of HDD-Type ultra-high density ferroelectric data storage. Thank you, Professor Cho.
Yeah.
Go ahead and you want to navigate? You want me to go back and good? Okay, they can. Oh, yeah. Let's see. Turn. Oh, here we go.
Yeah.
Okay, there you go. Want me to navigate the slides?
Yeah.
I break page up and down.
Yeah.
Yeah. Start whenever you're ready.
Yeah.
Yep.
Thanks for the kind introduction. Yeah. So, let's start. The research motivation the motivation of study. And anyway, so as you know, we're anyway, but total global amount of data is now increasing day by day and year by year. And it is expected this year it will reach 103 zettabytes, of which 90 zettabytes must be stored in mailing, as you know, mainly in data center. And of course, as you know, in data center, magnetic hard disk drive is mainly used as a storage device. And but now the decoding density, air decoding density is now little bit saturating due to the physical limitation caused by the existence of the super paramagnetic effect or existence of the exchange force in magnetization, as you know well. And but to solve such problem, now hammer and mama technique have been proposed, and also hammer is now in practical use. But even after introducing this technology, but we cannot escape from the restriction of the physical law, existence of the exchange force in magnetization. So we think novel data storage technique are required for the future information technology. And this figure shows the comparison between the ferromagnetic domain wall and the ferroelectric domain wall in the case of the crystal material. So in the ferromagnetic crystal, due to the existence of the exchange force, interaction exchange force, the a little bit thicker domain wall this ferromagnetic crystal has. On the other hand, in the ferroelectric crystal, there's no such interaction, exchange interaction force. So the domain wall, so the polarization suddenly can reverse. It is so the memory thickness very thin. Actually, after inventing our special probing technique, named scanning ammonia diode microscopy SNDM, about 10 years ago, we surely confirmed the wall thickness is very thin. It is a few lattice space. So we think ferroelectric material is a little bit favorable for the data storage application. And but also to apply the ferroelectric material for the data storage medium, it has a big problem. And this is a ferromagnetic material, magnet, and also this is a ferroelectric material. Anyway, ferromagnetic material has a polarization composed of the north pole and south pole. And if there is some particle in the atmosphere, but it exists as a dipole only. There is no single n pole and s pole in the world. So if outgoing field attract the such particle, but the outgoing field never screen. This is the reason why the permanent magnet exists in the world, and also ferromagnetic data storage is available because we can detect the outgoing field from the outside. But in the ferroelectric material, it also has a dipole moment, but it's composed of the positive charge and negative charge. And as you know well, charge exists as a monopole. So in the thermal equilibrium state, the outgoing field screened completely. This is the reason why there is no permanent electric. As a result, ferroelectric data storage is quite difficult because if we approach some detector, electronic detector, we cannot recognize the inside, find the state of the inside of the ferroelectrics. And with this background, about 30 years ago, we invented the scanning non-linear direct microscopy SNDM, which visualizes the electrical anisotropy of dielectrics and carrier distribution in semiconductor by measuring the capacitance change. And of course, this microscopy was initially invented for the ferroelectric polarization observation, which was invented about 30 years ago. And but as you know, the relationship stored charge in capacitance Q equal to CV. C is quite constant. This means nonlinear effect of the dielectrics is quite small. So to detect such a nonlinear effect in dielectrics, the sensitivity of this microscopy technique must be very high. Actually, finally, so as a result, this microscopy has a world highest sensitivity and resolution. Actually, measured capacitance detection sensitivity is 10 to the minus 22nd part per root hectode. This sensitivity is about 10,000 or 1,000 times larger or higher than the world famous scanning capacitance microscopy. As this microscopy has a quite high sensitivity, so we can use a very sharp tip and also operate in non-contact mode. It has a nano and atom projection. And now, as this microscopy technique has a quite high sensitivity, so the SNDM family, a lot of different types of SNDM family has been developed. For example, super high order SNDM which can detect the distorted capacitance response and detect the higher harmonics up to the 12 harmonics, or this non-contact SNDM and scaling non-linear direct potential can measure the atomic dipole moment of the sample surface with atomic resolution. And when we measure the semiconductor MOS metal oxide semiconductor interface, we can use a local deep level transient spectroscopy method. It is a modification pattern of the SNDM. And now we also developed a digital type SNDM named time resolved SNDM and so on. So now it is expected to have effective nanoscale evaluation technology for next generation material and devices. Anyway, so at first I'd like to introduce you the operation principle of this SNDM. This is the original conventional and analog type SNDM. Here is the SNDM probe, which consists of the so-called free-running active LC oscillator, whose oscillating frequency is tuned to this LC resonant frequency here. And the typical oscillating frequency in this microsphere is a gigahertz order. And the metal kit is connected to this tank circuit. And from outside, we apply the usually sinusoidal voltage between tip and sample. And by the application of the bias voltage, tip sample capacitance is modulated in the dielectrics due to the nonlinear effect, and in the semiconductor due to the modulation of the depression layer. And anyway, so tip sample capacitance is modulated. Then oscillating frequency is modulated. Whose frequency, as a result, frequency modulation signal comes from this SNDM probe, whose frequency deviation is proportional to the capacitance variation occurring under the tip. And by using the analog FM demodulator, we can convert the frequency deviation or capacitance variation to the voltage signal. And using a low intake amplifier, we can obtain the DC-DV signal as the SNDM data. And this is the one example of the SNDM probe photograph. This is the back side of the probe. You can see this is a metal coat cantilever here. And this is the inside of the SNDM probe. You can see inductance, and this metal area is a built-in capacitance, C0 and L here and here. And you can see a black two parts. Transistor, one transistor is act as the oscillator, the other transistor act as the amplifier of the oscillating signal. Anyway, so SNDM convert the local capacitance variation to frequency, and the most important thing is the signal to noise ratio. So it's a minimal capacitance sensitivity is about 10 to the minus 20 second per hertz order. Anyway, so here I'd like to explain how to detect the polarization by using SNDM. And this is a polynomial expansion form of the electric displacement as a function of the electric field, or stored charge or applied voltage. Anyway, P0 means spontaneous polarization of ferroelectric material. Epsilon 2 is a linear dielectric constant. Epsilon 3 is a nonlinear lowest order nonlinear dielectric constant. And epsilon 4 is a higher order nonlinear dielectric constant. And this number means rank of tensor. Anyway, invariant tensor, including linear dielectric constant, is insensitive to the direction of the polarization. But this epsilon 3 is a third rank tensor. So the sign changes in accordance with the direction of the spontaneous polarization, and also so by detecting this epsilon 3 using capacitance detection technology, we can obtain the information of the polarization, direction, and magnitude. Anyway, but to to detect this three, actually we apply the sinusoidal voltage or electric field to the capacitor made of the material we measure. This is a tip sample model, this capacitor. Anyway, so we apply the voltage to the capacitor, and if this material has a weak nonlinearity, alternate capacitance variation occurs. And this capacitance variation related to epsilon 3, which contains the information of the polarization, is directly proportional to the applied field bearing with the same angular frequency omega p. But the higher order response is proportional to the scale of the applied field bearing with the double frequency to omega c. So by using this frequency difference and also using blocking technique, we can simultaneously and individually get epsilon 3 and epsilon 4. And this is some example of the polarization measurement result by SNDM. This is all the data. Anyway, so scanning area is very large. But this material is very famous ferroelectrics barium titanate. And this is a two-dimensional image. You can see positive C and negative C. C means polarization is perpendicular direction. And this is A domain. A domain means it has a lateral polarization. Anyway, so this one-dimensional profile was taken along this A prime line. If tip is on the positive C domain with upward polarization, negative SLDM signal was obtained. And if tip is on the negative C domain, SLDM signal is positive. But if tip is on the A domain, the signal becomes 0. This means that if tip is on the A domain, there is a crystal symmetry along the depth direction. This means that there is no odd rank tensor component along this depth direction because it has a crystal symmetry. So if tip is on the A domain, the signal becomes 0. Anyway, so this is also AC domain structure of the PZT film. It also has the same crystal symmetry, tetragonal symmetry. And the left one is simultaneously measured AFM topography, atomic force microscopy topography. This is a SMBM image. Anyway, so you can see the similar AC domain structure, but this material is thin film. And this is a magnified image. And we selected this area and obtained the magnified image. You can see a domain structure and the negative C domain area. And also we select this area and obtain the magnified image. You can see magnified domain structure here. Anyway, so this one-dimensional profile was taken along this A prime line. And if you define the resolution of the microscope, this SMDM, when we measure the ferroelectric domain in ambient condition, the resolution is sub-nanometer order. So the resolution of SMDM is sufficient to resolve the very tiny bit, small bit, if we use ferroelectric material as a data storage device. And also, when we measure the semiconductor material and device, for example, when we measure the silicon 1117 atomic structure, we can measure the atomic dipole moment of the surface. In this case, the measurement was done in the ultra-high vacuum circumstance, and also SMDM is operated in non-contact mode. And also, this is a graphene on silicon carbide substrate. You can see this very tiny hexagon is the benzene, actual benzene structure of the graphene. And also, this SMDM is applicable to evaluate or measure the carrier or dopant profile of the semiconductor, very tiny semiconductor device. This is a cross-section of the three-dimensional flash memory. You can see surrounding gate is here, and also this line profile was taken this prime line on the surrounding gate. And so we can resolve the very small carrier profile with a resolution of the 1 nanometer order. So SNVM is applicable for the state-of-art next generation semiconductor device designed by using the nanometer scale design rule. And so anyway, so then we started the study on the ultra high density ferroelectric data storage about 20 years ago. At that time, of course, we used a scanning non-direct microscope as a read-write device, and also we used a lithium tantalate single crystal as a ferroelectric data storage medium. And these are fundamental research results. Using the ferroelectric data rate storage system based on SNVM, we formed a very small tiny nanometer drop with the size of the 3 nanometer in diameter. If we can form another bit in the vicinity of this dot, the memory density will reach 80 terabits per second. But actually, this is very tiny dot was formed by using a very thick tip with a tip diameter of 50 nanometer, like this. So if we apply the electric field here, the two dots are merged, unfortunately. Anyway, so, but we also try to store the actual information. This radiated phase is composed of the positive and negative domain dot, and the bit size is about 12.8 nanometer corresponding memory density is 40 terabits per square inch. And also, we confirmed the very fast switching characteristic. In this case, we apply the 500 second voltage burst to the medium, and we succeeded to reverse polarization. This means that, in principle, the writing is possible by using but in this case, we have to use a very thin material. And but also, the data storage has a problem. It's a reading speed. In this experiment, we conducted the readout test using hard disk drive type SLDM data storage system. In this experiment, we read the rotating periodically fold domain pattern on the spindle motor, and rotating speed is like this. Anyway, we succeeded to detect the clear signal, reading signal, but signal reading speed is 2 megabps, quite slow. And so this figure shows the comparison between the magnetic recording and direct recording. In magnetic recording, as you know, material is a ferromagnetic material, and we use ferroelectric material. And the writing method is, of course, in magnetic recording, magnetic field is applied, and we apply the electric field. And the reading method in magnetic recording, magnetic registration is used, and we use SNVM technique. And most important advantage of direct recording over the magnetic recording is memory density. And the writing speed is almost comparable, but the reading speed is quite inferior to the magnetic recording. So we think that to improve the reading speed is a top priority issue to be solved. And so 1.5 years, probably I already presented here new reading method. This figure shows the principle of this new reading method. About 4 years ago, we measured the temperature characteristic of linear dielectric constant and non-linear dielectric constant of lithium standard zinc crystal. Of course, linear dielectric constant obeys the Curie-Weiss law. It is inversely proportional to Tc minus T. Tc is the Curie temperature. But surprisingly, non-linear dielectric constant has a very strong temperature dependence. It is proportional to the minus 3.5 R of Tc minus T. So this means that if we approach, if the temperature is approaching to the Curie temperature, quite large non-linear dielectric constant can be expected. Of course, the reading speed of the SLDM method is proportional to the signal to noise ratio, and the signal is proportional to the magnitude of the nonlinear dielectric constant. And so last time as I told you, we proposed a new reading method, a heat-assisted pellet reading. We call this technique HAFA. Anyway, so this is a local instantaneous heating by laser irradiation. The mechanism is very similar to the HAFA in magnetic recording. But due to the short time heating up, so this method does not sacrifice the retention characteristics. If we assume the temperature of the material at 550 degrees Celsius, 2,500 times larger non-linear dielectric constant is expected. So in principle, BPS order reading may be possible. And this is a fundamental investigation result. And this blue line is a waveform of the applied optical pulse waveform. And this is a orange line is a SNVM output signal. So by the optical pulse irradiation, clear increase of the nonlinear dielectric response was observed. But unfortunately, due to the restriction of the laser and the other equipment, at the time, the time is very slow in the millisecond order. And also, if we realize the high-speed reading system, we have to increase the carrier frequency of SLDM probe up to the millimeter wave order, for example, 60 gigahertz. And also to read the domain information at the gigabps order speed, we have to increase also the frequency of the applied voltage to detect the nonlinear effect up to the gigahertz order. So we need a millimeter wave demodulation technique and also gigahertz order phase detector. And I'm optimistic because now for the application of the beyond the 5th generation and the 6th generation communication technology, the communication electronics maker now succeed to develop such a high frequency communication part of a device. So in the near future, we can obtain such a very small and high frequency device a little bit easier. But now, not impossible. And moreover, if we increase the oscillating frequency, some advantage is expected. So sensitivity of SLDM is proportional to the square of the oscillating frequency of the probe. So now we use the 1 gigahertz probe. And if we increase the frequency at 60 gigahertz, 3,006 times larger sensitivity can be expected. So high speed probe at gigabps may be possible. even if we don't introduce a half-a technique. But anyway, now impossible. So, we'd like to surely confirm the non-secondary capacitance of a nonlinear direct response can be detected in principle. So we conducted the high-speed playback proof of the possibility experiment after that. And in this case, we cannot obtain the millimeter wave probe, so we use the usual 1 to 4 gigahertz probe. And instead of using a rotating periodical pole medium, we measure the not rotating material, and instead of negative reading, we apply the pulse light. So in this case, continuous light is sufficient. So we don't need actual in the actual bus. We don't need a pulse light. But in this case, we apply the pulse light with the duration from the microsecond to nanosecond, and also we don't have the such high frequency demodulator, so we directly acquire the microwave signal by using the side of a gigahertz oscilloscope. And also, we don't have the such analog modulator. So after acquiring the raw data, numerically we demodulate the equilibrium signal, and we confirm the microsecond or nanosecond output signal. And at first, we constructed the hardware, and so in this case, we introduced a new laser pulse system, and the pulse duration can be varied from 1.5 microsecond to 1 nanosecond, and the frequency is about from 66 kilohertz and 100 kilohertz. So the duration of this pulse laser is less than 10%. And the wavelength is 458 nanometer, and use any of the range is 0.28. So especially the beam diameter is about 2 micron. And so this is a laser system, and here is a material, and this is here is a SMD probe. And we use the 1 gigahertz SMD probe. And you can see just the point end of the metal tip, the laser is irradiating like this. And we use this oscilloscope to acquire the microwave signal directly. And also to demonstrate and time average. So we newly developed the time-resolved SLDM system specialized for the high-speed playback proof of possibility experiment. And this figure shows the principle of the time-resolved SLDM system. So we directly acquire the microwave signal by using the digital oscilloscope. And after acquiring the data, the microwave signal is numerically demodulated. And this method has a quite high bandwidth, so we can have the quite high speed capacitance variation. And this is a shot of the PC display. Anyway, we use the 1 gigahertz probe in this experiment, and at first, this microwave signal is directly acquired to the digital oscilloscope, and then this is a waveform of the detected microwave signal. So you can see period is 1 nanosecond. This means the signal is 1 gigahertz. And then we demodulate. numerically and obtain this signal. In this case, to extract the low frequency part, we use the low pass filter numerically. And this bright light green waveform is actually measured laser pulse waveform. And this red line is, in this case, we use the low pass filter. So we set the low pass filter parameter like this. And in this case, a period is 10 microseconds. Anyway, this is a linear direct response. And by taking the time average, we obtain the linear direct response with after the noise reduction with the signal to noise ratio signal. And so this is average linear direct response. And if this is also measured laser beam waveform, and this means 70 milliwatt and 1 microsecond laser pulse is irradiated to the sample. And then we change this filter to the band pass filter and obtain this waveform by setting the filter condition. And the period of this waveform is 50 nanoseconds. This means that we apply the AC bias voltage with a frequency of the 20 megahertz. So this is a nonlinear direct response signal. But actually, we have to detect the envelope of this nonlinear direct response. So using a doubler and low pass filter and taking a square root, we actually obtain the envelope of the nonlinear direct response. Anyway, so this is surely half a signal for optical heating. And then we, using this system, we conducted the high-speed proof of possibility experiment bearing the light pulse duration from 1 millisecond to 15 nanoseconds. Because unfortunately, due to the restriction of the hardware, that we could not apply the higher frequency of the AC bias voltage. So we set the AC bias voltage at 20 megahertz. This means higher shorter part less than 50 nanosecond is meaningless. And this equation shows the capacitance response. This is a linear direct response as a function of the temperature or laser irradiation. And this is a nonlinear direct response. Nonlinear direct response, this is a magnified or amplified nonlinear direct constant by the laser irradiation. But to detect the nonlinear direct constant, we also apply the voltage, AC bias ratio of DC bias voltage between different samples. So we individually detect the linear direct constant response and nonlinear direct constant response. But to detect the nonlinear direct response, we must apply the voltage between different samples. And in this case, 1 microsecond laser pulse is applied, and the left one is this red curve is a linear direct response, and the right one is a alpha signal or nonlinear direct response. And of course, you can clearly see the increase of the signal via laser application. So we reduce the pulse with this at 500 nanoseconds, and even at this speed, we can confirm the waveform. But due to the large heat capacity, it has a little large time constant to cool down. Anyway, so but we increase the speed or we decrease the period duration of the pulse. So very sharp optical pulse is applied like this, and the signal to noise is getting a little bit worse, but we surely confirm the alpha signal. And so we think that we have to succeed to detect the non-second level non-linear direct response by alpha technology. And then if we reduce the pulse duration down to 50 nanoseconds, what happens? And but alternate voltage application is meaningless. But the DC voltage voltage can be applied. So if we apply the DC bias voltage, and if the nonlinear constant increase, we can detect this term as a linear dielectric response. So, あらら、あら、あら。
Some network speed.
Okay, yeah. So, oh.
Presentation back up here if need be. But I would goes to the next slide.
Yeah. Oh, yeah.
Try sharing from this side if that helps. Trick it. Here. What's there? Yeah, you just almost need one of those power up bars. And so, yes, I'm ready. I can try sharing from here if you want. Is it working on yours, Chris? No, it's not. Well, I can share from mine. Why don't I do that? Okay. So this is not, you're looking at, well, you should look at my screen if you switch it to Teams. Oh. No. I want to there. Let's see. Okay, that's my mouse moving. Let's see if I can change it. So you'll have to tell me when to change slides.
You can pass the mouse.
Yeah, that's true.
You go, try going.
I'll try. Next page.
Oh.
Oh, so you'll have to navigate.
I'm controlling this. Sharing.
Okay.
Sorry.
So
Can you just get on your laptop?
but pointer is can be used.
Let's go drop.
So this is output of the linear capacitance response, and this is frequency change. And when we apply DC bias voltage, in this case minus 10 volt, a little bit larger frequency change was detected. Yeah. So oh.
You want the next one?
Just back. Yeah. So this means surely by the application of the DC bias voltage, capacitance increase was detected. This means that even at this speed, the Harvard technique is possible. Please, next slide. And then we deduce the pulse duration 5 nanoseconds, but in this case, we cannot detect this part. And but at least this system is applicable for the nanosecond order capacitance response to be detected. So we try to detect the linear capacitance response at the speed of the 5 nanoseconds. So please. Yeah, next, please. Yeah, next, please. And but we this is not half a signal, but at this speed we surely detect nanosecond linear capacitance response. And next slide, please. Okay, next slide, please. and then we like to try to 1 nanosecond response, but as long as using a 1 gigahertz probe, 1 nanosecond means the frequency is 1 gigahertz. So as long as using a 1 gigahertz probe, 1 nanosecond response is impossible to detect. So we change the frequency of the probe at 4 gigahertz. And then we try to detect the linear capacitance response. Please. Yeah, next. So at this measurement, the signal to noise ratio is quite worse, but at least system is work at the speed of 1 nanosecond. So we confirm the 1 nanosecond response can be detected using our time resolved system. Okay, next slide, please. And this is a summary of the difference between the Haffer and the Hammer technique. The magnetic recording method of Hammer is, of course, magnetic recording. In our case, direct recording. And writing irradiation time is different. Hammer is writing, Haffer is reading. And in Hammer technique, near field light must be used because the bit size and the heating spot size must be almost equivalent. But in our Harvard technique, the resolution is determined by the resolution of the SNDM. So we don't need to use near field light. Converging light with lens with the diameter is sufficient. The micron is sufficient. Okay, next slide. So as long as permit my presentation time, I continue to my talk. And next, I'd like to talk about the trial fabrication of the inexpensive large area single crystal light recording media. Next slide, please. And as a realistic recording medium, we need a high quality, large area, and low cost, and mass producible material media. And for high quality, is single crystal light is preferable. And for the large area, next thin film, we need to fabricate the thin film media. And next, low cost. At low cost, usually we fabricate a very high quality single crystallite electric thin film. We use strontium titanate single crystal as a substrate, but it is quite expensive, and also we cannot have the very large scale substrate. So in this case, we'd like to use a silicon substrate. And next, For mass produced, we directly use a spotting method for the film growth. Next. So fabrication of single crystalline thin film recording media deposited on the silicon substrate by spotting method is we think the realistic media. So next. And so as a single crystalline ferroelectric material, we chose a PZT thin film because now in the semiconductor company or industry, not the single crystal, but many polycrystalline thin film for the FE has been deposited by sputtering method. So we have a lot of experience to draw the thin film of a visit thin film, and also okay. So we fabricate the PCT thin film on the 8-inch diameter on the silicon wafer, and left is the photograph of the used spotting equipment, and right one is a stack configuration of the fabricated PCT thin film on silicon substrate. Next. And this is a photograph of the PCT film on 8-inch silicon wafer. This area is, I think, the sufficient for the hard disk drive application. And the next. So we fabricate the 3 types of the PCT thin film with a thickness of 100 nanometer, 50 nanometer, and 30 nanometer. And at first, this photograph is a cross-section of this sample, and a little bit large distribution of the thickness was observed. And the next. And also, this is a cross-section of the 50 nanometer PZT film, and also a little bit large distribution of the thickness was detected. And the next, please. And this is a 30 nanometer PCC. Also, a little bit large topographic distribution was observed. And the next, please. And then we try to check the polarization reversal characteristics by applying the DC bias voltage to the film. And in this case, in the 3-point center, middle, and outer, we applied the DC bias voltage of -5 volt. Then we applied +5 volt in the smaller area, and then we switch the applied voltage to the -5 volt again in the much smaller area. But in this case, we don't have the good polarization characteristics. Next. And in the 50 nanometer PZT in the center area, a bit good polarization reversal characteristic was confirmed. And the next, and in the 30 nanometer PZT in the almost all area, we confirmed there a little bit good polarization reversal characteristic like this. So we chose this 30 nanometer PZT for the trial experiment to form the nanodomain dot. Next. And this is the result, one result. So anyway, this is a trial experiment. So let's start.
Oh, sorry.
Yeah, no problem. So you can confirm a smaller nanodomain dot formed on the PZT film, but we have to continue this work much more. And next, and this is a final topic. And we just last month, we started the first trial of the singlet direct recording for the realization of practical high density data storage. Next, please. And at first, we write a single track, singlet reversal pattern. And that first pitch was selected, left one is a 200 nanometer, but in this case, not single domain though. And we reduce the pitch was 100 nanometer, right case. So in this case, you can see the single domain pattern, and bottom one is a line profile of this image. And next. And also we reduce the pitch 50 nanometer and 40 nanometer. The stability of the system is not so good. So, but we confirm the surely singlet pattern was observed. And next. And finally, we reduce the domain pitch down to the 20 nanometer. In this case, around just below the 20 nanometer domain pattern was detected and observed, but our final aim is about 8 nanometer for the tentative pass range. So we have to continue this work more and more. And the next. And finally, we try to the triple track singlet experiment, just one result. And in this case, the smallest domain size is almost the same, 16 nanometer in diameter. Okay, next. And this is a final PowerPoint view graph. This is my dream. This is a roadmap of this drive type correct data storage. And now 2025. So I expect the entry of the company into the practical application research in this year. And after 8 or 10 years later, we'd like to realize correct data storage in practical use. Okay, next. Thank you for your kind attention.
You open it up for questions.
Yeah, we got a couple minutes for questions.
I saw you on the figure you had 3 nanometers as the smallest bit you're going to make. And then you said on the same image you had, same slide you had 12 nanometers.
Okay.
So what is, I guess 3 nanometers is your theoretical limit. What is the practical limit based on those 2 slides? Meaning, what is the limit you feel will be the smallest you can get?
Actually, in both cases, we use a tip with a very thick tip, actually, but it's a available metal coated AFM tip. The tip diameter is 50 nanometer. Okay. So we can form the one single 3 nanometer diameter reverse polarization. But if we apply the electric field in the vicinity of this 3 nanometer size bit, the electric field spread much more. So as a result, 2 bits are merged. So actually, to separate the 2 bits, we need a 7 nanometer. Actually, yeah. And but to store the actual information, we need at the distance about 12 now.
So if you use sputtered film, which is not going to be single crystal, so you will have dislocations, you will have, grain boundaries and things like that, which usually provide high conductance path for pre-charges, right? And you also heat up when you are reading. So do you have any idea what that does to retention of the information?
Please proceed.
Forward.
Forward. What?
I know.
What?
I had it to you, it's a wired connection now.
What? So, of course, we apply the, heat, some shrinkage of the bit occurs. What? Next. Yeah, next. So, so we, yeah, okay. Yeah, okay. Yeah. Please, next, please, next. Yeah. Yeah. So, about, in this paper, we measure the Arrhenius parameter for the shrinkage as a as a function of temperature. And using this Arrhenius parameter, we calculated the shrinkage ratio as a function of the heating time. The next. And so this is the data pulse width. And if you allow the 1% reduction, this line, and 10% reduction, this line. And if you'd like to read the domain bit 401 million times, so about the 10 microsecond duration is sufficient. But if you read the 1 gigabps reading speed, this time is sufficient. This means 10 to the 11th times we can read.
So the PZT data you showed at the end?
This,
Yeah, I know, but was that using laser or was that just standard SNDM? And the sputtered films?
Ah.
You showed the tracks?
yes,
Yeah. That's normal
Yeah,
SDM.
yeah.
Yeah. All right, I think we're at the end of our time. So thank you everyone for listening. Yep.